Well, good afternoon, everyone. Welcome to the final session day at DevWeek. Hope you'll be able to stay awake after a decent lunch, but I will try not to put you all to sleep. This session, growing configurable software with expression of T. Just a quick hands up, just to start things off. How many people have used expressions in the .NET framework? Wonderful. Why are you here? Fantastic. No, that's brilliant. So, we're going to show how you can grow software with expressions and grow software with expression trees. First of all, a little bit about myself. I am commonly referred to as a technical architect and evangelist. In truth, I'm a code monkey. I'm a code monkey. I'm proud of it. And I've been developing professionally for about 25 years plus. But I suppose I really started on these things back in the 1980s, when my first machine was a Spectrum, before migrating to the BBC Micro, and then onto the Amiga. God, what a machine that was. What a machine that was. Before eventually moving to the dark side. And moving into proper development, as it were. Although it really did feel like a step backwards at the time. So that's my background, really, and like I spoke, most of you people here pretty much language agnostic these days, switch between various different frameworks. I'm a very infrequent blogger. If you find anything, though, that is of any use, hey, brilliant, but don't expect any updates for huge lengths of time at periods of time. I'm also the world dual monitor speed reading champion at the moment. You see, I managed to train my eyes to move in different directions. Anyway, so we're going to start by, I've got a demonstration application, and what we've got is a large set of data that we're going to filter using a strategy. And so I'm just going to quickly walk you through what's involved with that. And we'll then take the filter pattern and we'll transfer it into functions, so a func of T. And from that, we will transfer it into an expression of func T. Okay? And then we'll look at compiling the filter to a method. So we will be using the strategy pattern to build code and compile it and store it on the file system and then retrieve it later on and use it later on. But we'll walk you through the steps to get there. So first things first, all of this code is up on GitHub. If anybody wants to put it down, you're more than welcome. The address is also in the slides. So yeah, it's at Ed Courtenay expression demo on GitHub. So the data source I'm using is something called GeoNames. This is brilliant. I don't know if anybody's ever come across this. It's an open source data set of features, countries, populated areas, all the way around the world. Really, really useful. And there's a nice big data set. It's a cracking thing to work with. So GeoNames has various classifications that it uses. Now, you can't see it from there, but let's quickly go in. Let's pull it up. Here we go. So one of the things it allows you to do is allows you to pick up locations. And some of these locations can have feature codes associated with them. And what we're going to be doing is we're going to be filtering the data that we've got by some of these feature codes and so by things like populated size and things like that. So in particular, we're going to be dealing with what they refer to as populated areas. Where are we going? Here we go. And bingo, come on. Well, you can see the amount of information you can pick up. I can't even find it now. There we go. So they've got various things, so you can pick like, you can get geographic locations and you can filter by populated places or cities or various other things. So that's what we're going to use as a data source. And the data source itself is simply a text file. It's a tab-separated text file. So we're not going to deal with it as a text file. We're going to read the data, transform it into an object, and then filter against those objects, okay? So the process flows, we're going to read the data in, and we're going to expose the data through as an enumerable of an geolocation data. So that's my representation of each line of data within the data file. We're going to apply a simple filter to it, and that simple filter is going to use what I'm referring to as a European configuration, and I'll go into that in a minute. And we're just simply going to count the results. That's all we're really going to do. But hopefully this should demonstrate what it is that we're doing. Okay, so enough slides. Let's bring up some code. So the application itself, you'll notice, has three real constituent parts. First things first is the CSV data source. So this has an embedded copy of some of the GeoNames data. This is their 15,000 city names. And so that's just been embedded in, and we're going to walk over this. There is another version of the data file which they call all countries, which is something in a region of over about 8 gigs, I think it is. So I'm not going to walk over that one. But this is all checked into the GitHub repository, so you can actually just sort of open it and run it straight away. Okay, so here is my embedded data source. So my embedded data source is just simply going to read through the contents of a file and parse it and present each line as an IGA data location. Okay? The next part to this is the filter. So I'm going to start with the simple filter here. Now, this will be given a configuration, and given the configuration, what it's going to do is it's going to filter by the country code, it's going to filter by the classification, and so this is the populated area. Are we looking at a city? Are we looking for a town? And we're going to filter by the modification date. So let's just quickly run this so you can see what this looks like. It's not the world's most interesting application, but it does work. So there we go. It's run. There are 172 matching records, and it's taken a certain amount of time to run. So that's basically all we're doing. So using that filter, we have an application that is called a counting application. Okay. So that's taking our data source, is taking a filter, and it's simply going to run through each line. And so here we go. We've got the time operation here. So we start a stopwatch. There we go. So all I'm going to do is I'm pulling the locations from my data source, and I'm counting given a filter function. Okay? Everyone with me so far? Excellent. So, as I say, when we run this, we've got 172 matching records. Now, the problem that we've got with this, if there is a problem, is that, have a look at, I didn't show you the configuration itself, did I? Sorry. So my European configuration is this. So I have a list of country codes. So what I'm saying is I'm interested in any of the lines of data where one of these country codes matches. I am interested in any, there also has to be either a city, town, village, or other agglomeration of buildings or the capital of a political entity. I want to see that there's a minimum population size, and I want to make sure that the data that we're pulling has been modified after the year 2012. Okay? So these are the rules that we're providing to the filter to be able to filter the data. Okay? So the idea is, obviously, that the rules can be supplied at another point, or the rules can be taken from any provider you like, and you can apply them through the filter and filter your data down. Okay? So, let's go back to our simple filter for a second. What's the main problem with this approach? So the main problem with this approach is that every time I'm applying the filter to a line, I've got to go back to my configuration. I've got to go back to my configuration object and say, what's my list of countries? Or what's the population size? Or in fact, if you noticed, the population size property in my configuration was a nullable type. So I may or may not want to filter on a population size. So I've actually got to go and check to see whether I've even supplied a value. So if I look at the configuration for the minimum population size, or filter by population, here, I've actually got to check whether the configuration minimum population size has a value. And if it has a value, then I actually need to return whether the test is passed, or I'm going to need to return true. Okay, because otherwise, how am I going to be able to deal with this? Okay, so for every single time we're running through, we are re-examining the configuration. And we're going back to a configuration object. Now, hopefully, these configurations will be cached. But you can see that this is a fairly inefficient thing to do. And so to have to go back and look at our configuration object every single time and say, have I got a value here? To then do a test against. Okay? So, what we're going to try and end up with is a situation where this doesn't happen. Okay? Any questions so far? Nope? Brilliant. So, let me go back to my application. Set up. So, I've got my accounting application module. So, I'm just going to unbind this. This is using Ninject, by the way, to construct the application. I'm sorry, because I just find it so it's nice and easy, so I can just bind stuff back into the application. I can completely change the way it works. So that was my simple filter. This now is a function filter. So this is the same idea, okay? But all I've done is I've changed the, I want to bring up my simple filter. Right, so in these cases, I just had methods that I was dealing with. I was just saying, here is a filter by country codes and execute it each time around. Now what I'm doing is I'm building up a set of functions and concatenating them in as one object to return back. And this is a bit more complicated to read, but actually it's pretty much the same sort of thing. So again, we have the modified date expression. Again, we have a population expression here. And again, we've got to check to see whether we have a value. And if we have a value, I'm going to return a function this time, not just a result. I'm going to return the function of an geodata location that returns a bool. So I need to return the case where the test actually happens, or I need to return a straight true. Okay? So I'm returning this back as a function. Now, if I execute this, it does exactly the same thing, filters the same amount of objects. It is slightly faster. It is slightly faster because I've been able to produce a single expression or a single function that's been combined in one go. So it's had a look at the configuration once, okay? And it's built up a set of functions, added them together, and returned that, and now my filter, my counting application, can run through that function. It's still slightly inefficient in the respect that it's got some of the tests will be going straight to a return true, but it is slightly faster. So we're going to take the function idea and turn this into an expression system. So let's just quickly go back to the slides. Here we go. Right. So our simple filter is possible, but it's difficult to cache the rules. You know, you've got to make sure, especially the way it was set up originally, you had to evaluate the configuration every single time. And so, as I say, the configuration settings were evaluated on every pass. Well, that's not ideal. So, let's take a sidetrack. What are expressions? Expressions are code as data. So the idea is that you have code that is expressed as data. So you can build code at runtime effectively. Does anybody ever use Lisp here? Anybody comes from a Lisp background? A bit? No. Okay, well, Lisp itself is a language that is defined as data. So Lisp code is in fact data that is expressed as code. It's an odd concept, but it's a useful one to get your head around. But expressions, certainly in .NET terms, an expression is a single operation. Okay, so it's an evaluation. So is something greater than or equal to? We'll come into them, and they can be combined together to form trees of operations. So think of things like the XML DOM. Everything in the XML DOM is an XML element of some form, or an X element if we're now dealing with X document. But they can be combined to produce much larger constructs. And so again, expressions are the same thing. Start very small, but you can build them up into larger trees. Hence the name of the talk, which was growing configurable software with expression T. So these are, I'm not going to go into them in much detail, but here we go. There is a whole raft of expression types within the .NET framework. So everything from binary expressions to dynamic expressions, default expressions, lambda expressions, loop expressions, member expressions, the list goes on. And just from the binary expression type, for example, this is where you'll get things like binary arithmetic on things like add, divide, bitwise operations, comparison operations, conditional operations. So, what is 1 plus 1 as an expression? How would you expose the idea of adding 1 and 1 as an expression? Where would you start? Okay, well, if you start from the add, okay? So we have an add operation, and then we have on the left-hand side operation, we have a constant of 1, and on the right-hand side, we have a constant of 1. This can then be compiled down and evaluated, and will produce for us an expression. It's pretty much as simple as that. Obviously, it gets a lot bigger, but that in its essence is an expression. It is the start of an expression tree. So, we're used to dealing with lambdas. We're used to the idea that lambdas are in fact funcs, or can be transposed to funcs. So how do we take a lambda expression, like this one here, and how do we turn this into an expression? Anyone? There's a one-line change, two-line change. No? Okay. The first line here at main, we've got a func defined as a func, which takes a foo and returns a string. Okay? To turn that from a lambda to an expression, you do this. Do this again. So there's the lambda, there's the expression version. It's as simple as that. So what we're saying is that the expression, so there's the same lambda there, So foo goes to foo.name, as in our previous slide. But all we're doing is we're wrapping the func of foo with an expression. Now, the .NET compiler is nice and clever at this point, and will say, I will build a tree out of this for you. And to then execute it, what I then have to do is I then have to get a function out of this. So I take the expression and I then compile it. So that will then give me, that func there, which is in fact now a func that takes a foo and returns a bool. And I can execute it. And that will do exactly what it says in the tin. That will just produce the name of, it'll just emit the name foo. But don't think everything can be converted. This looks, on the face of things, identical, except that we're using return semantics with a block as opposed to a single inline lambda. That will not compile. When you're doing this, you must deal with single atomic operations, or things that can be expressed as a single operation. And the return on a block just simply can't be done, because the compiler doesn't know how to break this down. So, common limitations of this approach are that you cannot convert a block of statements as to evaluate to a single expression. And the expression that you're dealing with can't contain assignments. Okay? But apart from that, it's actually quite easy. Now, you'll come to a point where you think, I want to combine the expressions I've got. So I've got a set of, I have a set of conditions that I want to all together, for example. All right? So in code, you would write this as, I have an expression, and I'm going to OR that with the next thing, and I'm going to OR that with the next thing. Now, obviously, that's no longer a single item. You've no longer got a single point of entry. You've now got 3 items that have been strung together. So as an expression form, what you would do, you combine this by saying, okay, I'm going to start with an OR, and then my left-hand side, I'm going to have my first expression, and then my right-hand side, I'll have another OR, and then I'll have the second expression that I'm testing, and then the third expression that I'm testing. Okay? Any questions? Does this make any sort of sense at all? Ish. Okay. Well, look, let's go back to the code for a sample, for a session, and let's have a quick look at what we're doing. Hang on, where am I? In fact, no, before I do that. Actually, no, I'll do it this way around. So, what I'm going to do is I'm going to go back to my counting application module, and I'm just going to uncomment this one here. So here is another filter, and this time it's an expression function filter. So I'm taking the functions that or the function types that were in the previous function filter, and I'm now going to express these as an expression of data location to bool. So, here we go. Again, here's the configuration being passed in and stashed away. There's the get filter function, which returns. Now, what this is doing now is this is saying, there's the expression to build up. Okay? So I'm going to use the country code expression, and the features expression, and the population expression, and the modified data expression. And I'm going to combine them. And then what we'll do is, to get that out to that form, I have to compile it. So that's the same step that we were doing in the slides. Okay, it's simply just taking the expression, compiling it down to a function, and then executing it. Okay. Now, not a lot has actually changed here. If you look at the methods, there's the population expression again. There's the modified data expression. We're still testing to see whether we have a value. We're still returning a lambda, and we're still saying we're still returning the condition if that hasn't been set. And the only difference is the signature. The only thing that's changed there is that. So as opposed to returning a func that returns a bool, I'm returning an expression of that func. Okay? And I have a single operation that can be, that can be expressed in either case. Okay? So once we've got those expressions, what we're dealing with up here is we take each one of them in turn and we AND them together. So this is an extension that comes from LinkKit. Who uses LinkPad? Brilliant. If you don't use LinkPad, use LinkPad. It's a fantastic tool. Even if you're not going to use it for testing or testing databases or connections of that nature, just simply for writing code straight off without having to fire up an entire IDE, it's priceless. But one of the packages that it comes with is a thing called LinkKit, which simplifies the operation of working with expressions. Now, LinkKit itself is also a NuGet package, so you can download it and use it separately. But it originally comes from it's the predicate builder stuff that comes from LinkKit, and it's really simplifies it, because if you have a look at what the AND is doing at this point, that's fairly horrible. So it's building an invocation expression. It's invoking, it's basically invoking an expression on one side, invoking an expression on the other side, and then taking the result and wrapping it in an AND also. It is pretty horrible. Writing this by hand, it's so error prone. So yes, LinkKit is well worth it. As I say. So that's pretty much it. So we are taking the functions, we are combining them together as expressions, we're then compiling that as a function, and we can now run this. So let's see what happens when we execute. Yep. So, same thing again, we've still got 172 matching records, and it's still faster. So each time round, we are actually getting some speed improvements. It's not bad. And there isn't a lot of work involved in getting to this point. But we're still at a position where we're dealing with a configuration. I just don't want the configuration to be involved anymore. Once the configuration's been done, once we've evaluated, I don't want the configuration to hang around anymore. So let's go back to our application. And this time around, we're going to go to an expression filter. Now, here's our population expression. Can you read this at the back, by the way? This makes it right. Okay. So there's our test. We're saying if there's a minimum population size has a value, we either return the function or we return the true statement. The true statement is a function, and we're returning this as an expression. Now, what if we want to build this from scratch? Okay. Well, we would start with a greater than or equal, and on the left-hand side we have a property. That property, if we go back, is this. It's the population. And on the right-hand side, we have a constant. Now, this is a constant. It's a value that we take from configuration, but once that's there, it doesn't change. How many times have you written? How many times do you ever see systems where business rules or things like that change during the lifetime of the application? We just don't, do they? We write configurable software. We allow the systems to be configured in this way, but once the system is up and running, during the lifetime of the application, these things are static. They're constant. Okay? So what if we can provide a way of generating this constant and then using it at that point? So here is the same thing rewritten as a straight expression. So we are returning an expression dot greater than or equal. And on the left-hand side, we have an expression property. So I will take the population out of the population value out of the location that I'm evaluating against. And on the right-hand side, I'm going to test this against the minimum population size. That is the same thing as this. Okay? But once this is done, once that's been evaluated, that's now a constant, and there is no more, and what will be emitted will have no reference to the configuration. So I have generated an expression, I've generated code from a configuration, but once that's done, it's no longer there. So, let me go back to the application, and there's my expression filter. So, if we run this, it's faster again. It's faster again because I'm now in a position where I only include stuff in my tests that are required, okay? And the entire expression itself has already been sorted. It doesn't, once the expression's generated, it doesn't need to go back to configuration and say, what's the population size I'm testing against? It knows there is a population size that is defined, right? If we had turned around and said the population size that we're testing against, actually we don't care, we do put a null value in there, it won't even emit the test. It won't even emit that section of the expression. So you see, if I go to my expression filter, here we go. So here's our configuration coming in. There's our get filter function. Again, this all looks very similar, and it should do. There's our get filter expression. And we're going to build the expression. And the building expression, what I'm doing is I'm simply returning an enumerable of expressions and adding them together. And I only yield the bits of the expressions that I need to yield. So I only emit bits of expression that are required as per my configuration, okay? And then I simply add them together. Now I've got some, you might find some useful stuff in here. There is some extensions that I've got here that do the operation of adding the expressions together in the same way that the link kit stuff. This is purely for dealing with straight expressions. So this is just simply combining with an operator. So I can combine a list. I can combine an enumerable of expressions with a function, a combiner there. And in this case, so if I'm doing an OR, the combiner is an expression or else, starting with a false, or if I'm doing an AND, the combiner is an AND also. So it builds that tree that I showed you earlier, starting from an OR, there's the left hand, adding another OR behind it, the left hand, adding an OR behind it, left hand, right hand. So this does this for you. Again, as I say, this entire project is on GitHub. You're more than welcome to download it, more than welcome to fork it, do whatever you like with it. Read it, burn it, throw it in the bin, whatever. So, we have an expression filter. So, we can go further than this, though. So this has produced a function in memory. Now, what if we were to do something a bit more clever? What if, go back to my roots program here. Got a love resharper. Here we go. So, here is an assembly generator module. Now, this application uses the expression filter that we've just built. And what it will do is it will take the expression filter, apply a configuration to it, generate the filter from this from configuration, and it's going to persist it to the file system. Okay? To do that, all we do is we get the filter, we get our filter expression. There we go. So I'm just going to use an assembly builder. So generate an assembly, I generate a module builder, generate a type builder, and then I can put a static method into the type builder, and I'm going to call the static method a filter static there. And the signature of this static method will be that it returns a bool, and it has one parameter, and that one parameter coming in is our IG, or data location. So I'm going to take the expression that we've got, and as opposed to simply compiling it so that I can run it, I'm actually going to compile to method. So I'm compiling it to a method, and I'm putting it in the static method that we've defined. And then I'm going to save it. So let's do that. So that appears to have done nothing. It has, in fact, done something else. How many people ever used to use Reflector? Brilliant. How many people know about the .peek? Good. .peek, I think, is brilliant. It's done by, it's written by the same people who write ReSharper, and it's free. So here is the test assembly that I've just written. In fact, so let's quickly go back to the code. You'll see there is a definition, test assembly. And inside the test assembly, you will find a test type. And inside the test type, there is the filter static. And there is, decompiled for your viewing pleasure, our filter. So all the countries that we listed in our configuration have now been compiled down into an expression and stored as a function on the file system. And what I've also done is, because I've also produced a filter, a sort of an interface wrapper that gets me to the static. But there you go. And just to prove that this is actually what we're doing, let me quickly go back to our application. Let's go to our European configuration, and let's change these country codes. Let's change it from that, and we'll just say that we want UK or, oh, I don't know, France. Okay? So I'll run this. Okay. Go back to there. There's our test assembly. Hopefully it will pick up the fact that I've changed, and there we go. So there is our expression compiled to a method, persisted to the file system, and stored. Okay? Now, so what I can do now, if I just quickly reset this back. There we go. So I'm just doing it twice because I can never remember whether I'm looking at the release version or not. Okay, so this is back. So what we should find now is this has gone back to the much longer test. There it is. Notice I'm not cheating with this at all. The comparison I'm using is a string comparison with an invariant culture, null case, and all the rest of it. So the same that I'm using everywhere. Now, let me go back to my application there. Okay. Sorry, helps if I run it in release mode. And there we go. So, did I uncomment that last? No, I didn't. So I have another binding here, and what this one's going to do is pull in the configuration that we've written to the file system. Okay? That's system activated, brilliant. There we go. So I'm going to create an instance of test type, test assembly. And I'm going to put it into a filter implementation bridge. And all this does is say, given this type that I've been injected into, push it out. And I can now treat this as a filter in the same way that everything else can be treated. Okay. And if everything works as according to plan, bingo. There's our filter implementation bridge. This has used the method that was generated, persisted the file system, and executed in that way. And it's still faster again. It's still faster again. I suspect what's happening is that is .NET's enginning the DLL that's being emitted. I'm not entirely certain at this point. But every single benchmark I've ever written against this, it's still faster to compile to method and then execute that way. Everyone with me so far? Any questions at the moment? Nope? Okay. How are we doing for time? Okay, so why bother? Well, as I've said, how about encapsulating your business rules? How about encapsulating business rules as part of a build process? How many times have you written software that is used by multiple clients that only really differs by configuration? No one? Lots of people? I see a few heads nodding. I've certainly done this. And you quite often then have to ship a configuration file that goes with your application, that goes off to the client then tinkers with it, and they muck it up, and you then have to debug the fact that this is what's gone on. Well, you could have the business rules expressed, let's say, as an XML document for your client, and use expressions to build up some rules, compile it in, and ship it as part of the application to your client, couldn't you? And as I pointed out before, rules rarely change during an application lifetime. Once rules are established, once the application's up and running, they rarely change. Okay? So, the other big one is, how about this? How about a domain-specific language parser? How about taking something that you can express as a rule set, as a string, for example, decompose it, and then turn it into something that can be executed? So, the example that I'm using here is the reverse Polish notation calculator. How many people know what reverse Polish notation is? How many people don't know what it is? Okay. Have you ever, okay, so this is a way of writing mathematical statements in what's called a postfix form. So we're used to writing, 2 plus 2, 2 plus 2. But the problem with this is that you have to now know the precedence of operations. So you have to know that, for example, 2 plus 2 times 3 actually is 2 times 3 plus 2, because because of BODMAS, the multiplication takes precedence over an addition. Okay? This is what catches all the kids out. So what this does is this puts the operation behind the values that you're dealing with. So in this case, we're dealing with 2 plus. So we're saying this basically you work back. So you push 2 onto the stack, push 2 onto the stack again for the second 2, and then when you come across the operation, you pull the two values off the stack and apply an addition to it. What you then do is take that result and push it back onto the stack again. So you can then build up more complicated structures. So in this case, 3, 2, 2 plus times is actually means multiply 3 adds 2 plus 2. So we're going to take the results of results of adding 2 and 2, and multiply it by 3. Now, notice that that looks extremely like an earlier slide. That looks like an expression tree, because that's exactly what it can be. So, let's write some code. And, yeah, let's actually use, right. Sorry, my brain just went numb. I'm trying to spell link with a K. Right, okay. So, what are we going to start with? Okay, so let's start with the expression that, or the formula that we want to calculate. Yeah. Let's start with nice and simple. We'll start with 2 and 2. Okay. Now I'm just going to get the tokens from this. So I'm going to break this down. So let's say tokens is equal to the formula, and I'm going to split it on spaces. Yay. And I'll just use string split options. There we go. Move empty entries. There we go. Okay, so all this is going to do is take our formula and break it down. So we're now going to get effectively an array of 3 items, 2, 2, and plus. So, now I mentioned that this works by dealing with a stack. So let's build a stack. The stack we're going to have is that. And let's just iterate over our tokens. So what we want to do is we want to see whether, first of all, is the value coming in a number? If it's a number, I want to turn this into a constant, and I'll put that constant onto the stack. Okay, so let's just say we'll have a double D. If double tripars D, sorry, tripars a token, then now what we'll do now is we'll take the stack, push, and we'll push onto it an expression constant. And the constant that will wrap up is this value D. Okay, so if we've been able to turn D into a numeric value, I'm going to take that D, I'm going to pop it into a constant expression. Okay, and I'm going to pop that on the stack. And we'll do then is we'll just simply continue. Now, the next thing I want to deal with, so that's going to be fine. I'm going to get 2 put on the stack, I'm going to get 2 put on the stack. Now, what about this plus? Okay, so we're going to need something to, some way of dealing with this. So what I'm going to do is have a map. I'm just going to have a simple dictionary. So var dix, or var map, equals new dictionary. And this will be a dictionary of string. And in the dictionary, what I want to get out is going to be a function. And I'm going to want to get a function out that, given a left-hand expression and a right-hand expression, returns an expression. With me? I confused myself at points with this one. Right, so this isn't that bad. So this is simply saying, in my dictionary, I'm going to store an expression, and the expression that I'm storing has to have 2 parameters. So it's going to have 2 inputs, and it's going to return, the result of executing is going to return an expression in its own right. So what I can now do is I can map add. I'll add a plus, and I will put into that expression add. And there you go. This expression add now fulfills this. So I realize I'm putting absolutely no error checking this at all. I'm just going to assume that if we get here, then the token's going to be valid. So I'm just going to get the expression that we're after. And I'm going to get this from our map, given a token. Okay? Now, what I said was that, and this is a binary expression, so what I said was that we're going to need to take the two items back off the stack. Okay, so we're going to pop them back off the stack and apply them with the expression that we got out of our dictionary. So I'm going to say, here's my left expression, so I'm going to take stack pop. And there's the right expression. And again, I'm going to stack pop this. Okay? Now, I'm going to push back onto the stack. Push. And I'm going to push on the result of executing this addition. So there we go, expression left, right. Now the idea is that when you've gone through all the tokens in a postfix calculation, what you should end up with is one item on the stack, and that'll be your result. So I'm going to take that. I'm just going to assume that the formulas that we put in are correct. And so I'm just going to take this and say that our result expression is equal to stack.pop. Okay. Now our result expression compile. Whoops. Now, hang on a second, I'm going to cheat because here's what I've written earlier. Yeah. So, I'm only doing this because otherwise I will always get this wrong. So what I'm going to do now is I build a lambda, and that lambda is going to be the result of executing that expression. And the result of that lambda is going to be the double. Okay? So I can now say lambda compile. And so let's assign that to a func. And I can func dump. Okay, so that should execute. That will execute this, which is in fact the result of the expression that we've got off the stack. And dump will just simply give us the result. Okay? Fingers crossed, nothing blows up. Bingo. And I don't know if you can see that, but there is the result. So we have taken a domain-specific language. In this case, we've taken a postfix representation of a formula. We've decomposed it into items. We've turned those items into expressions and combined them together. And we've turned that, and so that's now a tree, and we're now able to execute it and put it out to the outside world. So you can if you think about this, there are lots of things you could do with this. You could have business rules that are expressed as, say, formulas that are then generated and compiled at build time, shipped along with your application, and then passed on. I mean, I've seen, for example, some places, some retail stores have different definitions of what a franchise store might be, or how you would classify a store that sells women's items as opposed to men's items. Let's say you've got a chain of stores, and you want to be able to filter by, or you want to be able to provide a consistent way of defining how these things work. You've got one bit of software that you're shipping to multiple clients. Well, each client might have a slightly subtly different way of defining what a franchise store is, for example. So you could have configuration stored about your clients, how they define things. You could then build an expression at build time, compile it, and ship it. Client never needs to know. You've now got a configurable piece of software, but the client actually can't get in and muck things up, which I wouldn't say clients ever do much. So let's just prove things. So let's take this. So I've just added in a multiplier. So I'm going to need to say, let's just add in a few more operators. So map.add expression dot, can't type. So that's subtract. Let's add in a multiplier. There we go, let's multiply and divide. There we go. So now this should be able to turn around and say, so this will push 3 onto the stack, 2, 2, it'll take the operator there, it'll pull those 2 off, calculates 2 plus 2, or it'll just put an expression in, which will be an expression to add with 2 constants, and then it will then take the multiplier and then take that result and multiply with that. Which it does. If you look, one of the nice things with LinkPad is I can now take my expression. So if I take my result expression here, and I can dump this. And there we go. So there's my simple binary expression. This is the result of adding 2 plus 2 and multiplied by 3. So there is a node in there, type multiply. The right-hand side is a constant value of 3. The left-hand side is itself a simple binary expression. And that is the 2 plus 2. So there's a node type of add, and its left-hand side is a constant of 2, and its right-hand side is a constant of 2. Does that make sense? Yeah? So you could also do some much more complicated things. So, for example, I don't know if you know how you do, let's say we want to route. So I'm just going to copy this one here. Sorry. I'm not very good with Mac keyboards. I'm much used to using sculpted keyboards at home. I'm not very fast at these things. Okay, so I'm going to add in another operator here. So you can calculate a root, a square root or a cube root by multiplying a value by 1 over the value. So multiply by raising the power of a half, for example, will give you the square root. Raising the power to a third will give you the cube root, and so on and so on. So that you can express like this. So I have, there's my x and y, so there's the left-hand side, there's the right-hand side, there's a power, and there's the divide, 1 over. So I can now say that if I wanted to say I want the square root of, I don't know, 84, yes? If I've got this the right way around, what I should be able to do is 256 roots 2 should. Oh, hang on. I'm missing a brace somewhere. There we go. What have I done? Oh no, I knew this was a bad idea. Hang on. Oh, of course. Here I am talking about postfixing. Absolutely right. There we go. So I can use more complex, so I've used a token that represents a more complex expression and bound them up together. So this, in fact, is 2, and I've got this the wrong way around, haven't I? So it should be 256 root. The way I've done it. There we go. So 256 raised to the power of 1 over 2. And again, there we are. There's the node type. Node types of power. That contains a divide. And that can tell, and on the left-hand side there is a constant. And there's the other constant. But the thing to bear in mind is that once this is done, once the formula's been done, once the expression's been built, the source is no longer needed. So we can take either our domain-specific language or our configuration or anything that we want to deal with. Once we compile down to an expression, that's it. We don't have to deal with it anymore. Any questions? There's a hand there. Right.
Can that be basically a function? So I'm thinking, can I have an expression that actually gets a parameter like that one?
Yep.
Take the base, takes value, and returns that value.
Yeah, I mean, you can. Right. So if I go back to my expressions here. Ding, 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 ding. Where are we? There's the bridge. Sorry. Ding, ding, ding. Right, so you can use expressions to call methods on functions or things that you already that exist in your code base, for example. So here, I'm using this to call the equals method on string. Yes? And I'm even passing in, and even generating a constant there that says, I want to use string comparison and variant culture ignore case. Okay? So I'm not even just doing a straight equals here, I'm actually calling the method, the static method on string, yes, to do the comparison for me. So yes, if you have, you could have a library of functions that you're dealing with, and you could build your expressions to call library functions that you have. Does that sort of answer what you mean? Yeah. Anything else? Yes.
Can you do things like, say you've got a class that represents filters for a report.
Yep.
You can then transform the values in this class filter with an expression that can be used in an entity framework.
Yes. I mean, yes, absolutely. I mean, an entity framework. Linked to SQL, for example, is simply an interpretation of an expression tree. There is no reason why you couldn't take an expression tree and pass that into Linked to SQL, for example, or pass it into Entity Framework. So yes, you could build dynamic expressions to then dynamically generate against your ORM if you really wanted to. I mean, I suspect that might be a nightmare to debug. But yes, yeah, absolutely. There isn't any reason why you wouldn't be able to do that. Sorry, there was one at the back.
Oh yeah, I was talking about the uniqueness of a constraint. Say, for example, if we are talking about trying to match based on a variable like age or
Right.
we need to write all the combinations, or it just like we should find a unique constraint first, saying that find by age or compare the age only, and then age becomes a variable kind of.
Oh, right, I think I see what you mean. Yes, you would need to do this up front, and because the problem is you can't, or it's not easy to capture variables outside of the expression. So you want to be able to turn what you've got into things that you're dealing with. Do you see what I mean? You can do it. There are parameters that you can deal with. You can pass variables in. You can build entire blocks. You can build, you could build a function that generates a sequence of Fibonacci numbers if you wanted to.
Basically, so for example, if 18 years is the minimum age for voting, basically.
Right.
Right.
Yep.
18 should be a constant rather than a variable for me.
Precisely. Which is why, if you look back at what we're doing here, so that age 18. Right, would be a configuration detail, right? So somewhere you have a provider that is providing you with a configuration, right? And one of the values in that configuration is a minimum voting age. So in this territory it's 18, in that territory it's 21, okay? So what we're doing is we're saying, so for example, with the population expression, because this is exactly what we're doing here. What we're saying is, there is the value that I want to test against. Turn that into a constant. So I capture that value at this point. That's now a constant. That's not going to change. And now that's a constant, I don't need a reference to my configuration anymore. Because remember, when we go back, when we look at the compiled code here, when we look at what's happened here, there is no reference to the configuration at all. The only type that it cares about is the geodesic location that we're actually testing. Yes? The configuration has been examined and has been projected into this form.
So basically, if you have a bigger range of data, for example, to compare against,
Yeah.
rather than writing condition for each value,
Right.
should we just convert that into a range, or is there any best practice for
You could do it that way. You could write it in a range. You could have you could express a switch if you wanted. You could have much more complex tests as well. So this was an easy one to do because all I did was loop through the array of countries, express each one of those as an individual test. So I write the test for a single country, and then get an enumerable of those expressions, and then all them together. Right? Okay? Anything else? Any other questions? No? Oh yes, there's one.
You're writing an assembly to file.
Yeah?
Worry about permissions to do.
Yes. You don't have to write this to the file system. You could simply, I could quite easily have made an assembly builder, and I could quite easily have compiled that to an in-memory assembly if I wanted to, right? I could quite easily have stopped at the point of where I'm saying, here's the expression I'm just simply going to compile and just pass that around as a function, if you wanted to, okay? But it is interesting how much of a, even, so you have the upfront hassle of compiling it to an assembly that you're storing in the file system. But it is interesting how much faster it is at reading the data afterwards. And every single benchmark I've done on every expression that I've dealt with. And more often than not, the more complex the expression becomes, the more pronounced the difference is. Yes? Because the more tests that you're dealing with, or the more conditions that you're dealing with, sometimes I have found that the performance benefits are pretty extraordinary actually. And this is running on a, this is a fairly fast machine, so actually to be able to see any difference at all is quite unusual. Anything else? No? Okay. Sorry, I couldn't see. The light was shining in my eyes. Yes.
The performance is quite better, at least some percentage better. It's just under the expectation that you don't change any of the expression tree.
That's it. Yes. That's precisely it. Because, as I say, once this is up and running, your business rules aren't going to change. Using the voting age example, you're not suddenly going to have a change in voting age halfway through the lifetime of the application. Yes? Once that expression tree is up and running, once that expression has been calculated, it's done.
Do you have any performance of the compiling of expression trees?
Well, the compiling is very fast. I mean, again, it will depend. It will depend how. It will depend on the complexity of the tree that you're compiling. Generally, though, it's a once-off. If you bump this by, if you used a lazy implementation, for example, so a lazy over the function, yes, or whatever it is that provides a tree, you could then make sure that it's instantiated once and once only. Yeah, so you have a one-time hit. So I've done that a few times before. Yes?
Basically, it's kind of DSL, it's expression tree language. How expressive is it compared to C# as a whole, or its limitations?
Well, okay, so it's a damn sight more complicated to write from this form, right? I'm not in any shape or form advocating that you suddenly go and write your applications this way. That would just be lunacy. What I'm saying is that you can use this. And yes, if we go, there are huge numbers of types that you can deal with. If we just quickly go back a bit here. So these are the base types, or the base expression types that Microsoft provide. And you've got everything here from, block expressions. So you could, for example, have a block expression. That block expression is effectively a brace, C# brace, and that will contain a list of expressions. And you can have assignments, you can have variables, you can have loops, you can have whatever you want to do. But obviously, it's like writing a code DOM, it's like writing Roslyn, it's like writing with any of these things. The more it will get very complicated and very head melty very, very, very quickly. The larger you go. But yes, you can express if statements. You can express, pretty much anything that you can express as a test or a function. All the major things that you do day in, day out can be expressed as an expression. And also, don't forget, you can call into methods and methods that already exist within the .NET type system. Yes. So, like I did with with calling the equals method on string. Yes, as opposed to simply assuming that an equals is going to do the type of string comparison that I'm after. Okay. Anything else? Any other questions? Okay, well, I think that is about it. So, yeah, there we go. There's just an example of a much more complicated expression tree that you would be able to deal with. So, all the source code is available on GitHub. Please feel free to pull it down, tear it up, send me rude messages saying how awful it is. You're more than welcome. And the GeoNames information, so that's the GeoNames data source that I was referring to, you can get from there. I will add this slide deck to the GitHub repository as well at some point later on today when I get the chance. But that, as they say, apart from if there are any more questions, no? Then that is about it. Thank you very much for your time. The source is taking a filter, and it's simply going to run through each line. And so it's going to. So here we go. We've got the time operation here. So we start a stopwatch. There we go. So all I'm going to do is I'm pulling the locations from my data source, and I'm counting given a filter function. Okay? Everyone with me so far? Excellent. So, as I say, when we run this, we've got 172 matching records. Now, the problem that we've got with this, if there is a problem, is that, have a look at, oh, I didn't show you the configuration itself, did I? Sorry. So my European configuration is this. So I have a list of country codes. So what I'm saying is I'm interested in any of these lines, any of the lines of data where one of these country codes matches. I am interested in any, there also has to be either a city, town, village, or other agglomeration of buildings, or the capital of a political entity. I want to see that there's a minimum population size, and I want to make sure that the data that we're pulling has been modified after the year 2012. Okay? So these are the rules that we're providing to the filter to be able to filter the data. Okay? So the idea is, obviously, that the rules can be supplied at another point, or the rules can be taken from any provider you like, and you can apply them through the filter and filter your data down. Okay? So, let's go back to our simple filter for a second. What's the main problem with this approach? So the main problem with this approach is that every time I'm applying the filter to a line, I've got to go back to my configuration. I've got to go back to my configuration object and say, what's my list of countries? Or what's the population size? Or in fact, if you noticed, the population size property in my configuration was a nullable type. So I may or may not want to filter on a population size. So I've actually got to go and check to see whether I've even supplied a value. So if I look at the configuration for the minimum population size, or filter by population, here, I've actually got to check whether the configuration minimum population size has a value. And if it has a value, then I actually need to return whether the test is passed, or I'm going to need to return true. Okay, because otherwise, how am I going to be able to deal with this? Okay, so for every single time we're running through, we are re-examining the configuration. And we're going back to a configuration object. Now, hopefully, these configurations will be cached, but you can see that this is a fairly inefficient thing to do. And so to have to go back and look at our configuration object every single time and say, have I got a value here to then do a test against? Okay? So, what we're going to try and end up with is a situation where this doesn't happen. Okay? Any questions so far? Nope? Brilliant. So, let me go back to my application. Set up. So, I've got my accounting application module. So, I'm just going to unbind this. This is using Ninject, by the way, to construct the application. I'm sorry, because I just find it so it's nice and easy, so I can just bind stuff back into the application. I can completely change the way it works. So that was my simple filter. This now is a function filter. So this is the same idea, okay? But all I've done is I've changed the, hang on, let me bring up my simple filter. Right, so in these cases, I just had methods that I was dealing with. I was just saying, here is a filter by country codes and execute it each time around. Now what I'm doing is I'm building up a set of functions and concatenating them in as one object to return back. And this is a bit more complicated to read, but actually it's pretty much the same sort of thing. So again, we have the modified date expression. Again, we have a population expression here. And again, we've got to check to see whether we have a value. And if we have a value, I'm going to return a function this time, not just a result. I'm going to return the function of, here's what I'm referring to as a European configuration, and I'll go into that in a minute. And we're just simply going to count the results. That's all we're really going to do. But hopefully this should demonstrate what it is that we're doing. Okay, so, enough slides. Let's bring up some code. So, the application itself, you'll notice, has three real constituent parts. First things first is the CSV data source. So this has an embedded copy of some of the GeoNames data. This is their 15,000 city names. And so that's just been embedded in, and we're going to walk over this. There is another version of the data file which they call all countries, which is something in a region of over about 8 gigs, I think it is. So I'm not going to walk over that one. But this is all checked into the GitHub repository, so you can actually just sort of open it and run it straight away. Okay, so here is my embedded data source. So my embedded data source is just simply going to read through the contents of a file and parse it, and it present each line as an IGA data location. Okay? The next part to this is the filter. So I'm going to start with the simple filter here. Now, this will be given a configuration, and given the configuration, what it's going to do is it's going to filter by the country code, it's going to filter by the classification, and so this is the populated area. Are we looking at a city? Are we looking for a town? And we're going to filter by the modification date. Now, just quickly run this so you can see what this looks like. It's not the world's most interesting application, but it does work. So there we go. It's run. There are 172 matching records, and it's taken a certain amount of time to run. So that's basically all we're doing. So using that filter, we have an application that is called a counting application. Okay. So that's taking our data. Well, good afternoon, everyone. Welcome to the final session day at DevWeek. Hope you'll be able to stay awake after a decent lunch, but I will try not to put you all to sleep. This session, growing configurable software with expression of T. Just a quick hands up, just to start things off. How many people have used expressions in the .NET framework? Wonderful. Why are you here? Fantastic. No, that's brilliant. So we're going to show how you can grow software with expressions and grow software with expression trees. But first of all, a little bit about myself. I am commonly referred to as a technical architect and evangelist. In truth, I'm a code monkey. I'm a code monkey. I'm proud of it. And I've been developing professionally for about 25 years plus. But I suppose I really started on these things back in the 1980s when my first machine was a Spectrum, before migrating to the BBC Micro, and then onto the Amiga. God, what a machine that was. What a machine that was. Before eventually moving to the dark side. And moving into proper development, as it were. Although it really did feel like a step backwards at the time. So that's my background, really, and like I spoke, most of you people here, pretty much language agnostic these days, switch between various different frameworks. I'm a very infrequent blogger. If you find anything, though, that is of any use, hey, brilliant, but don't expect any updates for huge lengths of time at periods of time. I'm also the world dual monitor speed reading champion at the moment. You see, I managed to train my eyes to move in different directions. Anyway, so we're going to start by, I've got a demonstration application, and what we've got is a large set of data that we're going to filter using a strategy. And so I'm just going to quickly walk you through what's involved with that. And we'll then take the filter pattern and we'll transfer it into functions. So a func of t. And from that, we will transfer it into an expression of func t. Okay? And then we'll look at compiling the filter to a method. So we will be using the strategy pattern to build code and compile it and store it on the file system and then retrieve it later on and use it later on. But we'll walk you through the steps to get there. So first things first, all of this code is up on GitHub. If anybody wants to put it down, you're more than welcome. The address is also in the slides. So yeah, it's at Ed Courtenay expression demo on GitHub. So the data source I'm using is something called GeoNames. This is brilliant. I don't know if anybody's ever come across this. It's an open source data set of features, countries, populated areas, all the way around the world. Really, really useful. And there's a nice big data set. It's a cracking thing to work with. So GeoNames has various classifications that it uses. Now, you can't see it from there, but let's quickly go in. Let's pull it up. Here we go. So one of the things it allows you to do is allows you to pick up locations. And some of these locations can have feature codes associated with them. And what we're going to be doing is we're going to be filtering the data that we've got by some of these feature codes and so by things like populated size and things like that. So in particular, we're going to be dealing with what they refer to as populated areas. Where we're going. Here we go. And bingo, come on. Well, you can see the amount of information that you can pick up. I can't even find it now. There we go. So they've got various things, so you can pick like, you can get geographic locations and you can filter by populated places or cities or various other things. So that's what we're going to use as a data source. And the data source itself is simply a text file. It's a tab-separated text file. So we're not going to deal with it as a text file. We're going to read the data, transform it into an object, and then filter against those objects, okay? So the process flows, we're going to read the data in, and we're going to expose the data through as an enumerable of an iGeolocation data. So that's my representation of each line of data within the data file. We're going to apply a simple filter to it, and that simple filter is going to use